Kukusaki High School, Okinawa.
Hi, I'm Obi Mueller. I'm a freshman from Kukusaki High School.
I'm Natasha Hunter. I'm a junior from Seoul American High School.
I'm Scott Lovejoy. I'm a sophomore from Seoul American High School.
I'm Hanai Phillips, and I'm from Dakota High School, senior. And our title is Deiyaku Jitsu.
Okay, so first we'll start with the objectives we'll cover today. We'll cover to understand how to use Reiyaku Jutsu and the history of how they used it. And then we'll describe the definitions of Japanese words. And then we'll go over how and why the Japanese people in the Edo period used this method. So Wasan. So farmers use the calculations for agriculture and to count like how much crop they brought in like each harvest. And they used it for calculations of tax such as proration. And the merchants, they learned the mathematics which were necessary for their business and calculating prices and stuff. And then it was also used for money changing. And Teijutsu and Sanko, it was written in 1772 by Takabe Takahiro and explains the concept of finding pi through using wasan. So Reiyaku Jutsu, it's basically like a subgroup of wasan, and it's approximating the value of an irrational square root by using fractions that are close, like one that's less and one that's more. And Reiyaku Jutsu, its methods are used they're used without a calculator, so it's purely just pencil and paper, old school.
So we had two challenge problems, but the first one was to find the closest fraction equivalent to the square root of 73 by using the Reiyaku Jutsu method.
So, for example, we'll use a smaller number. Our whole class did this. We calculated the square root of 2 by using a small calculator that doesn't do the square root, that doesn't have the square root button. So we, and later on we'll describe it more in depth, but basically we picked a less than or greater than, and we had to do 1 less than square root of 2, less than square root of, not square root of 2, fraction of 2, and our answer is 1.4142, and that was the closest thing to square root of 2 that we have gotten, but this is our actual thing. We went through the whole process of getting that. So first we started off with 8.5 over 1, and then less than square root of 73, less than 8.6 over 1, but since we weren't allowed to use decimals, we went with up here, 85 over 10 is less than square root of 73, or 85 over 10 is greater than square root of 73. And we had to add those two numerators, 85 plus 86 over 10 over 10. And the one mistake that we've all made is that we try to find the common denominator at first, but that's not how you do it. That's not the Yakujutsu. So you add the numerator and the denominator. And we have gotten 171 over 20, and we kept repeating that. So as you see up there, we got 73.1025. And the closest number that we have gotten is 73.0075. We were okay with that answer, but I wanted like a more closer answer to 73. So I kept going and going and going, and I have found 72.9999. There was 2 numbers after that. Our professor or our helper said that that was good, but it would have been better if it was 72.9999 and like 89, but it was 72.999936. So he wanted me to keep going, but I kind of stopped there and yeah, it was 5 pages of that, and whatever.
The second challenge problem was to find whether or not the reduction method stopped with those two equations at the bottom by using the information given at the top.
Okay, so for our first example, we broke this into two parts so we could prove it. For our first example, we had a target value of 15/7. And so with that, we knew that 15/7 was equal to about, is this on? 2.143. And so with that, you know that it's greater than 2 and less than 3. So after that, you solve for P and Q using the formulas given, which was P equals D times F minus C, or D times E minus C times F, and Q equals A times F minus B times E. And so with that, you find out that P equals 6 and Q equals 1. So then you add the boundary values together, giving you 5/2. And with adding them together, you see that you use D over C Q times, which is 1, and B over A, you haven't used it all P times, which is 6. So you can anticipate that you need to use it 5 more times. Yeah, B over A and 2/1 are the same thing. Okay, so I continued step 3, showing the work of how I got 2/1 plus 3/1 to equal 5/2. And after that, you check if 5/2 is greater than or less than your target value. And since 5/2 was greater than our target value, we added the lower boundary value to our current value and got 7/3. And then we checked again if it was greater than or less than the target value. And since it was still greater than, we added 2/1 again. So, and you just keep going like this until you reach your target value. And since our target value was 15/7, we reached it after we added it 6 times. So you can see at the bottom, 3/1 was used 1 time and 2/1 was used 6 times, giving you P equals 6 and Q equals 1.
Since we're just going to give one more example to show or to answer our problem, these are just practice problems. So kind of glossing over what she said, this time we're going to use a harder one, doing 67/4, which we know is between 16/1 and 17/1. Using the equation you can see in the top left, you can compare the two and fill in the P equals and Q equals equations to find that P is 1 and Q is 3. After you add the B over A plus D over C together, you'll get 33/2, and then you've already added P once and Q once, so you only have to add Q 2 more times. And if you do that, you get 67/4 again. So from what we found, the answer is yes. We saw in our examples that the equations P equals D times E minus C times F and Q equals A times F minus B times E to solve our equations work, and it does end there.
Questions?
Questions?
How long did it take you to understand the process?
To understand it? For our problem, it took us
2 hours?
Mr. Sparks, a lot of Mr. Sparks, and just working out multiple problems to finally realize the pattern that we saw. Yeah, so it
2
took us
hours yesterday, and then we went over it on Monday for another 2 hours. So. Oh, sorry. Yeah. Heard us, right? Yeah.
Any other questions?
What did you guys have fun doing most?
yeah, figuring out the answer. That's
It
the best
feels
part.
really good to find the answer of a really tough equation, and when it all clicks and makes sense,
Yeah.
you feel really good and really smart.
Had any of y'all heard about the
not at
No,
all.
but in Japanese school, it's like they learn the history of it, but they don't actually use it. Well, obviously because we have calculators now. But yeah, they learn the history of it and like all the people and like who was involved, and they read the books of it. Like a high school student came in and like talked, had a presentation for us and explained the theories that they used and what theories they used. So.
As you said, now that you have calculators and all you have to do is hit that little square root button,
Yes.
you know, the answer just pops out for you. How does having learned this particular formula setup change the way that you look at your computations? When you look at, okay, something, square root of 2, right? Something small, but how does it change the way you look at it now and understand perhaps its background?
For me personally, it makes me like actually understand the math behind like how you get square root, because I never really thought about it. I knew that pi was some kind of a rational fraction and all that, but I never really thought about its application and how they actually found it, you know? So it makes me like understand and appreciate calculators, so yeah.
I'm also gonna add, it really shows how long these irrational numbers can be, because after lots of work, we were able to get a fraction close to about the first 4 decimal points of square root of 2, and they're infinite. It took us a while to get 4. So it just shows how big and long numbers.
Any other questions? Okay. Thanks again.